Okay, we talk about angular kinetic energy and moment of inertia. And in class, it took a long time to get through this, okay? Now, we have kinetic, we want an expression for the kinetic energy of a mass m moving with angular velocity omega along the arc of a circle of radius r. Okay, well, should be a quick answer to this. Okay, and there isn't, because in the first place, nobody seemed to know what the expression was for kinetic energy. The expression for kinetic energy is 1/2 mv squared. We have been through the derivation of this, and the class remembered that it has something to do with Vf squared equals V naught squared plus 2a delta x, and just putting aside the question where that comes from, which we need to understand. So, okay, we put this together with Newton's second law, and nobody could state Newton's second law, okay? Well, Newton's second law says net force equals mass times acceleration. Now, there's words around that. The net force of mass m is equal to the mass times the acceleration, with the simple rearrangement being that the acceleration is the net force divided by the mass. So if we put this together with this, we replace the acceleration here with the net force over the mass and do some simple manipulations, and we end up with F net delta x equals 1/2 mvf squared minus 1/2 mv naught squared. And this is the answer to the question of what happens if you exert a net force F net, constant net force F net, through a displacement delta x. So it's worth also saying that this is the answer. Find something of the right color here. Well, okay, I'll just use this. What's an effect of net force F net acting through displacement? Delta x. Here's your answer. So, conceptually, we just start with the idea, okay, I'm going to exert this net force through some displacement on some mass. Okay, maybe one of the carts, maybe I just push one of the carts. Probably want a more massive cart because it'd be pretty easy to push one of these, but if I want to feel some resistance, I push something 60-pound weight on wheels, push it with a constant net force through some displacement, okay, through 10 meters or whatever. This is what's going to happen. And this tells us what happens to the squared velocity. Now, another way of reading this is we conceptualize F net delta x is the amount of work we do. And if kinetic energy is 1/2 mv squared, this is a change in kinetic energy. So now we have the work kinetic energy, work equals change in kinetic energy. Now this is work by the net force, so maybe I should put a net on this. Okay, the work by the net force is equal to change in the kinetic energy. It's that simple. Very important idea that we're over this 2-3 weeks ago. Okay, we derived this and we stated this. We've also stated what happens if you exert a net force F net for time interval delta t. Constant net force for time interval delta t, what's that do? And that leads us to the impulse momentum theorem, which is not relevant to what we're doing here at the moment. Okay? So we have to understand this, because otherwise we don't have a concept of what this means. Okay, and we also need to run it through a number of different situations so that we see what good it can do us. then we develop a real understanding of it. If all we do is memorize formulas and use them, we're just doing mathematics, we're just doing arithmetic. We're not really applying physics, and we're not understanding what's really going on in a system. Okay, so we need to do that. Okay, so anyhow, kinetic energy is 1/2 mv squared for this reason and for this definition, and the reason comes from the answer to this question. We have to understand all that when we use kinetic energy. Okay. We don't have to. There are a lot of things we can do with kinetic energy that don't require the deep understanding, the superficial stuff, but if we want to do anything with any depth, if we want to solve a challenging problem, it's very helpful to understand all of this. Okay. So, now what's V? Okay, how are we going to, okay, this is an answer, but it's not the answer because you're given omega and r. You're given the angular velocity, which is the number of radians per second, and r, which is the distance of the mass from the axis of rotation, or at least the radius of the circle around which the mass is traveling. Okay? Well, we have to understand circles. And another thing that we ran into was nobody knew the definition of pi. So we keep getting wrong answers about how many radians there are in the arc of the circle. Of course, we didn't get good answers about what a radian was. So all this stuff needs to be tidied up, tightened up, and sorted out within the next 10 days or so, because it's going to be a test. Okay. So we now have to express V in terms of omega and r. Something we've done a number of times in class, but it needs to sink in, and we need to have some definitions. Okay, now one definition that nobody seemed to understand or know is that pi is the ratio of the diameter to the circumference of the circle. Okay, now I didn't write out all the words, but I'll write them now. And this is any circle. The ratio of how far around to how far across is always the same, no matter how big the circle. Something that a decent curriculum in secondary school and even middle school would address very effectively. Okay, I can't think of the right words. But to not know this and not understand these kinds of proportionalities, well, goes to the de-emphasis of geometry in the curriculum. Tragic error on the part of I don't know whom. I don't know who's to blame for that. Plenty of blame to go around, I'm afraid. Okay, anyhow, pi is the ratio of diameter, circumference of a circle. And what's a radian? A radian is defined by the condition that the distance of a point along the arc of the circle is equal to the radius of the circle. It's like an equilateral triangle, but bowed out a little bit so that one side forms a circle. A radian's a little less than 60 degrees. Now, it follows from this and this that there are 2 pi radians corresponding to a complete revolution. And answers I got were 2 radians. Okay, well, no. If you go all the way around the circle, it's more than twice, the distance you go is more than twice the radius of the circle. The diameter is twice the radius of the circle. The distance around the circle is clearly bigger than the diameter, lots bigger. Okay, 3 times, 3.1415926, and so forth times. Okay, so we know the 2 pi radians correspond to a complete revolution. We have to nail that down. That has to be part of the way we see the world. Okay. All this is background, and it was around a discussion of a beam rotating about an axis, and we were rotating the beam and looking at it. It follows that if omega is in radians per second, then at a distance r, each radian corresponds to arc distance of r. So, for example, if you're moving at 2 radians per second, you'd be moving a distance 2r every second. Okay, well, if we multiply r by omega, how many, well, the distance we are from the axis, multiplied by how many radians we go through in a second, we'll get how much distance we go through in a second. Because the distance along the arc is equal to the radius times the number of radians. So it's very easy to reason this out, as opposed to trying to memorize it as a formula where you never know if r goes in the numerator or denominator. At least not the day after the test, you won't know it. You reason it out. It's all something that can be easily reasoned out from basic principles and basic pictures of circles, basic geometry, basic interpretation of words. Okay, so make sure we've got this. Okay, well, with all that, then we say that, okay, V is going to be r omega. V's distance along the arc per unit of time. Omega's the number of radians per unit of time, which is a number of radii of distance per unit of time, and this all follows. Okay, so V equals r omega. The kinetic energy is 1/2 m times the quantity r omega squared, m f m v squared. Now everybody's good with algebra, so that's not a problem. And I chose to write this as 1/2 mr squared omega squared, saying this is a big deal. And I'll even go so far as to put some parentheses here. And then I'm going to say that this quantity mr squared is just what we can use with different omegas and calculate this as 1/2 times that quantity times omega squared, much like 1/2 mv squared. So this mr squared takes the place of m when we use angular quantities as opposed to linear quantities. Well, there's more to it, so we'll continue in a minute.